Have you ever wondered what it actually costs to ask an artificial intelligence to write an email or plan a trip? Every single time you type a prompt into an AI, real, fresh drinking water is consumed in the physical world to generate that answer. This puts us in a tricky spot because we desperately need AI to help us solve our biggest environmental challenges. Right now, smart farming systems use these algorithms to analyze exactly where a field needs water or fertilizer, cutting down on chemical runoff and boosting the amount of food we can grow. High above the Earth, satellites powered by machine learning scan the globe to instantly locate invisible plumes of methane leaking from pipelines, allowing us to plug massive greenhouse gas leaks that we otherwise would have missed. But as this chart illustrates, global AI water demand is projected to reach billions of cubic meters every year. For scale, look at the red line. The UK projects a daily water shortage of 5 billion liters by 2050, a gap this technology is widening. The very tool we are relying on to guide us out of a climate emergency is quietly draining the natural resource we need most to survive. To understand why this happens, we have to look at where the cloud actually lives. It doesn't float in the sky. It lives inside massive physical warehouses filled with endless rows of computers. Doing complex math billions of times a second generates extreme physical heat. To keep those processors from melting, facilities pump millions of gallons of clean water through cooling systems to absorb that heat and carry it away. Computer scientists are tackling this problem through a movement known as Green AI, which focuses on putting these massive software programs on a strict computational diet. We can't build our way out of this by just installing bigger air conditioners. We have to rewrite the software itself so the computers don't work as hard in the first place. The first major technique for doing this is called model distillation. Instead of using a giant power-hungry program for every single task, engineers use that massive teacher program to train a smaller, leaner student program. They transfer that knowledge into a much tighter package. By cutting away the bulk, the overall size of the software shrinks drastically, which means the computer processors have far less heavy lifting to do. These newly distilled programs run incredibly fast and require roughly 40% fewer processing steps, all while keeping nearly identical levels of intelligence as the original giant. Because this smaller digital footprint requires far less electricity to run, the physical servers run cooler, directly eliminating the need to pump millions of gallons of water through the building. The second method for trimming the fat is called pruning. Think of an AI like an overgrown tree. Pruning involves snipping away the digital branches, or data points, that barely contribute to the final answer, leaving only the strongest, most useful connections intact. Testing shows that systematically removing these weak connections can cut a large program's energy consumption by roughly 32% without making the final answers noticeably worse. Taking away that extra digital bloat stops the processors from needlessly spinning their wheels. A relaxed processor stays cool, and that keeps our physical drinking water sitting safely in its reservoirs. The final major optimization step is a concept known as quantization. Instead of making a computer calculate extremely long, complicated decimal points, engineers lower the mathematical precision. It is exactly like rounding a long decimal to a simple whole number, so you can do the math in your head faster. Doing these simpler, rounded calculations can actually cut the energy used to answer a question in half. We found that the software can achieve the exact same problem-solving goals with this lower mathematical precision, but because the math is easier, the hardware generates a fraction of the thermal heat. We have to remember the physical stakes here. With regions like the UK staring down a daily water shortage of nearly 5 billion liters, we simply do not have a drop to waste. At the same time, we desperately need these advanced algorithms to discover new clean energy materials and to perfectly balance modern power grids. We cannot trade our physical water security for computational speed. Genuine climate action means holding technology companies accountable, ensuring they implement these efficient, green software principles so that the machines we are building to protect our world don't accidentally drain it dry.